Tervetuloa johdatus automaatien teorian kurssille. Minun nimi on Ion Petre ja olen matematiikan professori Turun yliopistolla. Olen myös toiminut monta vuotta tietojen käsittelytieteiden professorina Turussa. Olen innoissani luennoida tämän kurssin sekä tietojen käsittelytieteiden opiskelijoille että matematiikan opiskelijoille. Luennoin tämän kurssin englannin kielellä, mutta keskustelu, demotehtävien ratkaisut ja loppukoe voi hyvin olla suomeksi. Automata theory has a long history in science. Its beginnings can be traced back to the 1840s, with the field being actively developed from the 1930s on. The topic is a central part of most study programs in computer science in the world and in many discrete mathematics programs for several reasons. It's a very simple model of computation. It's a good model for interactive computations, meaning a machine that reacts to its environment and leads its computation in response to the environment. And also it captures the iterative aspects of many different real-life processes, identify patterns in text or images, the steps taken in a medical diagnostic process, investment decisions, artificial intelligence, for example, as you see it in gameplays. It's an important foundation of computer science study programs because it introduces the concept of computing in a simple framework, yet capturing the essential features of step-by-step processes and that of the interaction with the environment. It's perhaps the most fundamental presentation of the concept of computational thinking. It's an important part of mathematics study programs because it shows a part of math that is very different than the traditional parts: calculus, algebra, geometry, topology, number theory, and so on. Even in the context of discrete math, it shows unique concepts such as dynamical processes and infinity. This course is a basic introduction to automata theory. It consists of two parts. In the first part of the course, we introduce two simple mathematical instruments to allow reasoning about iterative computational processes. And on one hand, we will discuss about structural inductions, for example, to enable reasoning about successful computations of an automaton. And in part of the course, we are going to introduce the key element of automata theory. We will discuss about regular expressions, which are central, for example, in pattern matching. We will discuss finite automata, for example, central in algorithmics, and regular grammars, for example, very important in compilers for programming languages. And I want to start with a very brief history of concepts and people important in automata theory. And the point I want to make is that automata theory, as we know it, came as a result of several different streams of motivations and concepts converging almost simultaneously to give what we currently call automata theory and formal languages. The roots of automata theory are traced back to the 1930s and 1940s, when there was a strong need to understand the concept of computation to be able to develop computing machines. But in fact, the foundations were already laid in the 19th century with contributions from Boole and De Morgan. And what they essentially did was a sort of algebraization of logic, allowing to operate with logical statements. And this was crucial, for example, for the work done by Claude Shannon on switching circuits, where the objective was to develop a computing machine that would calculate on binary inputs. And this was done around 1938. And about the same time as Shannon, we had also Alonzo George, Emil Post, and Alan Turing working on different abstract concepts of a computing machine. And their objective was to try to clarify whether mathematics is decidable. Meaning that if you are given a mathematical statement, you would like to know whether you can decide whether that statement is true or false through some sort of a generally applicable prescription, what we call today an algorithm. And working on this, Post and Turing came up with the so-called factory worker model, where the idea is that you would have a input tape feeding input to some sort of an elementary operational unit that only has a finite memory and can only read and change the current input cell. And this was supposed to resemble the idea of a factory worker that's working on a input belt and can only see the particular object in front of him or her and do something to that object, and then the belt moves with one position to the right, and the worker works on the next object. And in case of errors, the worker also has the ability to move the input belt one position to the left. There was also about the same time a different type of motivation, and that was the quest to understand the connectivity and the functioning of the brain seen as a network of neurons. And these neurons would be firing and they would promote the activation of their neighbors. And all of these were formalized through propositional logic, and the main proponents of this line of work were McCulloch and Pitts. This was work done in 1943. A little bit later, after the Second World War, we have in the 1950s, we have Kleene working on representations of events in such neural networks, and later on that was to become what we nowadays call regular expressions and use in a lot of work related to pattern matching. In 1956, again a different line of thought and a different motivation coming from Noah Chomsky. He is a linguist, and he proposed some mathematical structures to generate all sentences of a human language. And his idea was that he would like to understand the formal rules of what make correct sentences in a natural language, for example in English. And it didn't quite work out. It wasn't quite successful with human languages, but it turned out to be later on hugely successful with machine languages, opening the way to compilers and in general later on laying the foundations to what was to become software engineering. And 1959 we have this work done by Rabin and Scott on finite automata and their decision problems, and this in fact is the modern version of automata, and in fact the terminology that they proposed in this seminal paper is pretty much what we are also going to follow in this course. From the local perspective, Turku was one of the early world capitals of research in automata theory and formal languages, and this was due to Arto Saloma, an academician, one of only 12 at that time, and professor at University of Turku, who was an early pioneer of research in automata theory. He was responsible for introducing this topic in Finland, and worldwide he was very well known, for example, as being the author of the first good monographs in automata theory. There is this book that really helped spreading this topic quite a lot, Theory of Automata, published in 1969, followed a few years later by this book on formal languages, 1973, and even later on by another one, Jewels of Formal Language Theory, in 1981. As a curiosity, he also published later on some things about what computer scientists should know about sauna. This was in 1981 in the Bulletin of the European Association of Theoretical Computer Science. In this course, there are a few key concepts that we are going to cover. And on one hand, we are going to discuss about computations. And in this course, computations are going to be step-by-step, arbitrarily long processes in which we will see how the input is being processed step-by-step. And typically that's going to be in the form of some automata that we will define later in the course, processing their input. But we will also see computations in a different way, as a sort of a generative process. The idea being that you are generating an output step by step, and we are going to see that in the form of regular grammars generating an output. And finally, we will also see a different concept of computation in the way that we analyze a structure describing a pattern, and that's going to be in the form of regular expressions. And to do all of these things, we will first introduce a number of skills that we need to reason about such computations. We are going to need to discuss how to prove properties of all elements of a discrete infinite set. And the reason is this, that our computations can be arbitrarily long, and we will need to think about all these intermediate steps that our computations are going to go through. So proving properties of all elements of discrete infinite sets is going to be one skill that we need to build very early on in the course. And that's going to be done through induction, and especially structural induction. And one comment I have is that some of you may have seen induction in some other courses, maybe in high school math or in some basic courses of math. But in this course, we are going to build on that basic notion of induction, and we are going to, in fact, go to structural induction. And the difference is that we are going to discuss about how to how to define structures inductively, or if you want, recursively. This is another word used in computer science. How to prove properties about such infinite recursive structures, and also how to define functions on such recursive structures. And again, the motivation is we need to reason about computations, and computations are going to be, in some sense, such recursive structures constructed step by step from some basic elements. So we will discuss about this structural induction in a somewhat more sophisticated way than the basic notion of induction that you may have seen in some other courses in basic mathematics. And then is that we are going to teach this course with an emphasis on proving the correctness of our constructions and the correctness of the properties of our machines, of our automata. And this is, I think, important for computer scientists going towards computational complexity of their algorithms, discovering the limits of what can be computed efficiently. And we are going to see in this course, for example, deductive proofs of the type that you are used to. And the style is going to be, if something is known, then we prove something new using that knowledge. But we will also have inductive proofs that are particularly useful in computer science. And the basic idea there will be, if some basic elements are known, what can we say about all the structures that are obtained by combining those elements? Just to give you a quick example, if we know how an automaton processes single letters of the input, what can we say about all the strings it's going to accept, no matter how long they are? There will also be some other proof techniques in this course, such as proofs by contradiction or by counterexample, and equivalence proofs. And the point with formal proofs is, of course, to convince the reader about the validity of the argument. And the style and the level of detail can be quite different from case to case. But we will see many such examples in this course.